Welcome to today's video. In this video we're going to start talking about code constructs, and this will really start to get us into the primary goal or purpose of the course, and that is to being able to analyze an unknown binary in which we have no original source, and understand what it's doing to try to figure out the functionality and the purpose of those programs. Before we get in, I want to talk a little bit more about just some of the big picture, and in particular in analyzing code. And that the course is really designed to, we're going to get into some of these programs through the exercises and through the labs, and we're going to look at it instruction by instruction. And we're doing that to not only understand some of the instructions, because some of them are going to be very important to understand what that specific instruction or this group of instructions does, but also to better understand what the compiler is doing to the program, and sometimes how they change through what that original program was to what you're now seeing in the resulting binary, the resulting instructions in IDAPRO. In general though, and as you move forward, just be aware that oftentimes you're not going to go through every single line of a program in order to figure out what it's doing. You're just not going to have the time to do that. It's going to become very tedious and very time consuming, and that you'll need to be able to really focus on a function, focus on a section of a program, and generally being able to identify what it's doing without spending that time to go through it instruction by instruction. You'll be able to look at some code and see maybe function calls to modify the registry or function calls to do some networking, and you'll say, oh, I can identify that, and this is where it's making a socket connection, or this is where it modified the registry to add itself to auto start on log on so that it could remain persistent. And we'll start to set the foundation for that. And so there are a couple labs maybe towards the end of the semester where it'll be more important to get that general idea of flow and be able to pinpoint exactly what you need to understand in the program. But for the next few labs, we're really going to spend a lot of time going through things in detail. Now, to help accommodate for that, the labs and the programs are generally pretty short. And so that's how we will accommodate for that, and that we will focus on things in those labs through those programs that I feel are important. We'll also be focusing on C and C++, and almost every single program that I provide will be written in either C or C++, and then using the CL compiler, so the compiler provided from Visual Studio from the command line to build those. Now, the file extension is how that compiler knows what to use, whether to use the C compiler or the C++ compiler, so whether it's a .c or a .cpp, because you can use both basically for either one. There are some differences. And if I say, for example, I compile a C program using C++, that might change the resulting binary. It might look a little bit differently. And I'll make sure that when that's important to walk you through the things that are, where there are differences and why that is important, how that would affect or impact your analysis. Okay, one of the first things that we'll talk about today then is we're going to go back and we're going to revisit variables. And there's this big picture programming concept, something you're generally introduced to very early on, is the concept of scope, and that we generally talk about global scope and local scope. Global scope being a variable that can be accessed throughout any function within your program, and then a local scope being a function, or a variable that can only be accessed within a function or within maybe a control structure within that function. Something like an if statement or a loop. If you define a variable inside of a loop, it can only be accessed from within that loop. Right? Now, where those are actually stored in memory and how those look in IDA it's important to understand and recognize. And again, that's really the core of what we're starting to talk about now, is being able to recognize these constructs in IDA to be able to get a better understanding of how maybe that particular variable or that data is being used, so that we know how the program works. So in IDA, in assembly, what we'll see with a global variable is it's typically defined in the BSS or the data sections. And so if you think back to your assembly class, you chose what section based off of whether you needed to initialize a variable with data or you did not need to, and you wanted it uninitialized. And there's a performance impact on the two. What we'll see with IDA then is that those globally scoped variables will oftentimes be simply referenced by a memory address. And we looked at one last week, and that we had, for example, a move instruction. So move into EAX, dword underscore, and an address. Right? That's indicating that we're dealing with some globally scoped variable. The other one are the local variables, and those are going to typically be defined on the stack, although they can also be defined and used through registers. And so sometimes you'll see a function being called, and instead of a push before the function call, push meaning that we're putting data on the stack to pass values for the arguments for that function, you might see that data gets moved into a register. And then within that function, it's referencing that register instead of the stack. And it does that for performance reasons. But by and large, we'll be using the stack. And most of the programs, most of the examples, not all of them, but most of them will be using the stack. Now, when it comes to the stack and stack variables, how we identify those and see those is a little bit different. Whereas with global variables, we'll have a specific address in memory to that variable, right? It'll be a word or a byte or a D word in memory. When it comes to the stack, then we're oftentimes going to reference the location of that local variable based off of either EBP or ESP, so our base pointer or our stack pointer. So you'll see things like EBP minus and then 4, or EBP minus 8, or EBP minus some value. Same thing with ESP. You might see ESP plus 4, ESP plus 8, ESP plus some value. And what you want to think about when you see EBP or ESP being used is that you're calculating an address for a local variable. So that's the big difference between the two. We'll also talk about naming variables, and I try to do some of these core concepts over and over again just to help build that familiarity and some of the comfort with it. And naming is no different. We've been renaming variables now for a while. The primary purpose in doing that is to help us better understand the program and the purpose of that local or that global variable, so that when we start to look at these programs and these functions, we get a better understanding of how it's being used. Keep in mind, when you rename something, that renames that location in the database in its entirety, so everywhere that it's used. So it can help, it can have a trickle effect, especially on longer programs or longer functions. It can have a bigger effect for your understanding. You may rename it early on, and then later on in that function see that it's being used again, that same variable, and now you've got a better understanding of how that variable is used, the impact it might have on that particular function or the program. So you can click on the variable, and then you can either right-click and select rename, or you can press the N hotkey. And I typically just press the N hotkey because I think that's a little bit quicker. So we'll take a look at those. We have 2 example programs here. And the first that we'll take, we have several examples that we'll start looking at. So what we're going to start doing here in the upcoming videos is looking at a C program, and then I'll have compiled it, and we'll also look at that in IDA as well, so that the resulting binary in IDA. This is the code from example or exercise 2. And the only thing I did to modify it for today's video is I added another global variable, in which we'll take a look at that, and you'll see that it really didn't change how it's being referenced in IDA. But because we're talking specifically about variables, I wanted to come back and visit this program. As with anything we do, I encourage you to not only open up and look at the program in IDA, look at the binary in IDA, but also get comfortable with taking that program, taking that original source, compiling it, maybe making a few modifications yourself, and then also looking at that program in IDA. As far as the location of these, that is important. I want to point out that here is just my Finder view for our course material folder. So this is everything that you're seeing in the Google Drive. I have the code folder, and inside of there, I've broken that into 2 additional folders, dynamic and static. And this is kind of how you can look at the course. As far as the first half or so will be static, being a lot of time with IDA, and the second we're going to be more dynamic, and we're going to use debuggers. So we're in the static folder, and I broke these down even further, dynamic and static, just because we're going to have a lot of sample files. So I just am trying to keep some organization to the actual code that we're looking at. Inside of here, you'll see the source and the executable. So any example that we look at, I will provide you both the source and then the executable, the binary that we're looking at in IDA. So right now, exercise 1.c, you can see that's open, and ex1.exe, which is what I have open in IDA. Okay, so variables. We have a couple of globals, and we have global and global 2, and we have some locals. Int local equals 17. If we want to first identify these global variables, right, oftentimes what we'll need to do is try to find out where they're used in the program, because they're defined in the data section. So we're not going to see these defined in main. We're going to see them used in main, but we're not going to see them defined in main. I'm in main right now. And so in order to find that, probably the easiest thing to do at this point is to say, okay, well, if I want to look at global, I see global is initialized with a value of 255, and I can see that it's first used in this call to scanf. So if we go over here, we can see here's a call to scanf. Now, I'm using IDA Pro on my MacBook, and the interface looks just slightly different because just with the layout and the icon set and all that stuff. It also probably does a little bit better job in identifying some of those standard library functions, such as scanf and printf. And so I'm doing this just because it runs a little bit faster, and I think it's going to be a little bit easier than for me to bounce back and forth between a VM and the iLab and stuff. And so I'm just trying to make it a little bit easier. We're focusing on these instructions, and these instructions, regardless of the version you're looking at, should look the same. Now, if you think it's a detriment to you, if it's too hard to make the translation or it just doesn't look close enough, something's wrong, let me know, and I can either adjust or I can start using the iLab again in more detail just to make it a little bit easier. But for the most part, it should look identical. The only thing you'll generally have a problem with is in some of these standard library calls being identified. You can still identify those yourself, and I would encourage you, if your database, if your IDA does not identify the scanf, to identify it and rename it. Oftentimes, though, you're going to be able to do it by looking at how that function is being called. And if you see, for example, a scanf, you see a push offset AD, and what we're pushing is a %D, then that's a pretty good indication, because we know that with format specifiers, %D, %S, %I, any of those that you've used throughout the years for printfs and scanfs, if we're pushing that before a call to a function, odds are it's a printf or a scanf, and you'll be able to figure out, sometimes just based off of the context, based off of what's being pushed or passed to that argument, to determine what type of a function call it is. Okay. The other thing that can help, highlight these instructions. Highlight whether it's a call or whatever instruction you want to look at here on the left, and that'll highlight all instances of it. And so if we're looking at this original source, before we get to this if statement, okay, and this flow here, we'll talk about if statements today. This we can identify as a bunch of conditional comparisons, so likely an if statement. We can see that before that we have two function calls, printf and scanf. Here's our two function calls, call to printf, call to scanf. Two calls. Call is the instruction. It means we're about to call a function. All right, as far as the globals, right? So I want to call, we have this call to scanf, and before that, because we're going to push the format specifier and then the address to the variable that we want to use. In this case, this is a global variable. We'll see those two pushes. So there's the push for that offset right here, and then here's the push of that address. You can see dword underscore and then the address 414000. Because that's an address, we can double click it and it'll take us right up here, 414000. That's the address for that data. And you can see the name of that variable. That's a dword 255, initialized to 255, which is what we initialized here. Okay, this is probably in hex right away. So if you click it and then right click, you can convert back to hex, convert back to base 10. Okay, we can also highlight that label and hit N, and that allows us to rename. And so now if I rename that, it renames it here as well as everywhere it's used or referenced within this database. So now back up here on the navigation, okay, the back and the forward arrow, remember that's not redo and undo, that's navigation, forward and backwards. I click backwards to go back to where I was, and now you can see that that has been updated. That reference to that address is now global, but I renamed it, instead of dword underscore in the address. Okay, we can identify the other global. Initialize that with, or assign a value to that of 128 inside of main. And if we look at this, one of these first move instructions, you can see there's 128. That would have been 80 hex before I converted it. So highlight that, right click 128, and you can see it's very similar. dword 415F84. That's the address. And so if we right click on that, there's the address. You can see .data section, dword 415F84. It's a dword and it's a question mark. And what that question mark is telling you is that it wasn't initialized with any data. That is an address that points to a dword, 4 bytes, but there was nothing initialized, right? Which is exactly what happened here. I did not initialize it. So that's what you're seeing when you look at that question mark. If we go back to main, we can see now it's being assigned. And the move is how we do some of that basic assignment. We're saying move into that memory location 128. Okay, just like previous. Probably a good idea to go ahead and rename that. So global 2. Okay, as far as the local, here you can see I already renamed it, and what it would have been before, I can't redo it, so it would have been something like that, var4, var_4. And what you can see here is this is the difference. Now, we're using EBP plus and then this offset, EBP plus and this value, because we're referencing the stack relative to the base pointer, EBP, right? And so that's an indication for us, that's to clue in that this is a local variable and these are global variables. And those default values that IDA assigns those var_4, EBP plus var_4 or move global to, the fact that that's a direct address into the data section, that gives us a clue as to whether it's the global or the local. Okay, just like the global, I can highlight the var4, you already saw that, and I can rename it. I can say local. And now I have identified those three variables, the two global and the one local, inside of this database in this program for me. Right? And we know that because 17 is being moved into EBP plus the value of local, which is that assignment operation right here. Okay, we'll talk more about exactly how IDA comes up with these names a little bit later. So right now it's just important to be able to generally understand them and to rename them to help give you understanding of how the program works. Okay, here we have, starting with this compare, we're going to talk about compares today, but starting with that we have the if statement, series of if statements, comparisons that need to be made, the if and the else, and then once we're done, so all these blocks right here represent that, then this last block is our puts, printf, puts, and then the return, right? And we can see that because if we highlight that call instruction, we have puts, printf, puts, and then our return. Okay, so all of these last calls are just getting executing the puts and the printf for us. Okay, so that was just a revisit on the local and the global. So hopefully that starts to make sense and that you can identify which one's which by looking at how those addresses are being used inside of IDA. Okay, when it comes to arithmetic, we have many different types, many different operations that can be performed. And one of the things that you'll realize here as you start to look at the programs in IDA, the disassembly in IDA, is that the operations, they don't always disassemble. The instructions that the compiler generates aren't always exactly what you expect. So there's a handful of instructions that you're simply going to want to be able to just identify and generally understand what's going on. Most of them are relatively straightforward. We have add and subtract and divide and multiply. But there are some additional considerations with things like the division and the multiplication, as well as some additional instructions you might not be familiar with that are used before that type of arithmetic operation is executed. So one of those is CDQ, and CDQ simply doubles the size of the operand in register AX or EAX by means of sign extension and stores the result in register DX, AX, or EDX, EAX. Okay, so what that is saying is that if you say CDQ AX, it's going to expand the size of that through sign extension and store the result across these two registers, DX and AX. If we use EAX, then it's going to do the same, but it's going to expand across EDX and EAX. It's going to use both of those registers. It's going to sign extend. And remember, we have two instructions that you'll generally encounter when it comes to sign extension. You'll either have zero extend or sign extend. The zero extend doesn't care about the sign flag. The sign extend does, and the sign extend will preserve the sign flag. So in this case, if we need to make a sign number larger, we might see, or you might use the CDQ command. Now, I've added a couple of resources. I'm going to go ahead and close this IDA into our resource folder. So if we go back and look at the Google Drive, you'll see that there's a resources folder. And inside of here is the assembly book from 314. So if you just need a little bit of a refresher, it goes through those pretty succinctly and just giving you some examples and walking you through the definitions. I've also uploaded the Intel Architecture Manual, and this thing can be very, very daunting and overwhelming because it's thousands of pages of just raw instructions. But you can use it to help find and look up and get examples of an instruction that maybe you didn't see or didn't know. So maybe you're looking at a program in IDA, you come across CDQ, not sure what it is. Well, if you open up the instruction manual here, and I just did a search for it, you'll find I get a lot of results. It took a second here to find the one that I wanted, but here it explains sign extension. It says, okay, you can use CBW, CWDE, CWD, CDQ, convert double word to quad word, to perform sign extension to double the size of the source operand. Right? So it'll go through there and it'll help. So just wanted to provide you with some additional resources to help, when you run into a problem with an instruction that you don't know or understand, where you can go to figure out or get a little bit more information about that. Some of the programs we look at, I'll throw or ensure that there are some instructions in there that we don't specifically talk about, so that you'll have to do a little bit of research, because that's a big part of malware analysis or reverse engineering. So you'll have to do a little bit of research and find those resources on your own or through the things that I provide to help understand what that instruction does. Okay, IDIV and IMUL, or div and mul, those are the instructions that you'll commonly see when dividing or multiplying. And again, you need to understand or recollect that when you divide by, for example, a 32-bit source, division uses EDX and EAX. It uses both of those registers. And so if you see, IDIV or div by EAX, then both of those registers are being used. This goes through, and again, I'm intending this or hoping that this is largely a refresher, but this goes through and tells you exactly what will happen when you do division. All right, so IDIV or div, that's the common instruction that you'll see, and this is an example of the instruction itself. So if I say IDIV A, if A is 32-bit, so let's say it's EAX or EBX or ECX or EDX, and what it does is it divides the register pair EDX by EAX, EDX and EAX by A, and then it stores the quotient in EAX and the remainder in EDX. Okay, if A, so let's say our instruction is IDIV A, so IDIV AX. If A is 16-bit, then it uses DX and AX and stores the quotient in AX and the remainder in DX. Okay, if A is 8-bit, so maybe it's IDIV AL, then it restores, it divides the register AX by A, and it stores the quotient in AL and the remainder in AH. Okay, so the instructions might use certain registers or certain register pairs, as well as you need to understand the result of that operation, where it's going to store the results. Right? So in the case of division, it's important to understand that the quotient will be stored in EAX after the division, and that the remainder is stored in EDX after the division. Because we want to see what the program is using, what data it's using after that instruction is executed. Okay, so here are some examples, and hopefully these look familiar to some of you, because this is the register dump utility that I use in 3.14. If not, it's not a big deal, because we're just looking at data that's being stored on registers. The first example is we see move into EDX 0, move into EAX 30,000, and then move into ECX 5 with an IDIV of ECX. And so what this is doing is it's setting up the registers in order to divide 30,000 by 5. Now, because IDIV ECX, because ECX is 32-bit, we're going to use EDX and EAX in order to do the division. So you see here, that's why I moved into EDX a value of 0, because we've got to get that register prepared, because it's going to be used in the division. And if we don't zero that out, likely there's going to be data in there from whatever used it last, and it's going to mess up the results of that division. Okay, what did we say? Quotient is in EAX, remainder is in EDX. And so if we look at the results here, this first series of registers is just this dump regs function. Sorry, so that's just giving us the values of those registers immediately after IDIV is executed. So EAX is right here. You can see 1770, and EDX is all zeros. And if we divided 30,000 by 5, we would expect there to be no remainder. So no remainder in EDX, and the quotient is 1770. That's in hex. So we want to be able to figure that out in base 10. So if you open up your calculator, you can see I've got mine in programmer mode. Here is base 16. I can now type in 1770, because this is all hex data, and flip it over to the base 10 mode, and you'll see that's 6,000. And 30,000 divided by 5 is 6,000. Okay, the next two examples here are just to highlight why it's important to understand what registers are being used. and also to talk a little bit about sign extension and an example of the CDQ command. So here you can see, let's say I want to divide negative 30,000 by 5. And if I set it up exactly the same, the only thing that I change is that I make my move EAX a negative 30,000, the results are not correct. If we look at this register dump 1, this one in the middle, we can see here's EAX, it's it's a large number, and EDX has a remainder of 1. All right, we know that's the problem too, because even though this is a negative value, there still should be no remainder. Instead of 6,000, it should be minus 6,000. We can also see this value right here in EAX, and we know there's a problem with that, because if we think about and refresh, and we'll refresh here in just a moment, the 2's complement. 2's complement is how we store negative values in within the actual in memory, and so that should be a negative value. The quotient there should be negative, and if we look at the topmost, the most significant byte here, it's 3. That would be in binary 0, 0, 1, 1. Right? And the most significant bit then would not be set. So the sign flag would not be set, while the sign bit would not be set. So this isn't even a negative number, and it's wrong. Again, the reason why is because we're doing IDIV ECX. So it divided EDX and EAX by ECX. EDX was 0, EAX was 30,000, minus 30,000. So the registers were not set up correctly. So the solution is to do something like CDQ. So now if I move into EDX 0, move into EAX 30,000, CDQ will sign extend EAX into EDX EAX. So we'll go back and we can take a look at that. Doubles the size of the operand and register AX or EAX, depending on the operand size. Right? So it's going to, there's no operand, CDQ, it's going to double the size of EAX, sign extension, so in EAX I have minus 30,000. Okay, now I do IDIV ECX, and here we have the result. So EDX, no remainder, which is what we'd expect, and EAX has FF E890, which looks better, because looking at this number now and seeing that this hex digit is all 1s, that means that the sign bit, I shouldn't say the sign bit, but the most significant bit is 1, which in 2's complement means that that's a negative number. All right, so in order to really to prove that this result in the last slide, FFE890, is correct, that is, we're looking for a value of minus 6,000, we need to refresh on the 2's complement. So again, this is intended here as a refresher. So hopefully the 2's complement, even though it may have been a while since you've last done anything in 2's, it's just you'll remember how to do it pretty quickly and pretty easily. So the method that I take, generally speaking, is we've got this value here. So this hex value, FFFE890, and we want to see what that looks like in 2's complement in base 10, right? So we want to do the conversion. So first thing I do is to take all of those hex digits and write them down in their corresponding binary. So hex F would be 1111. Recall that each hex digit is 4 bits, right? We have the numbers, the values, possible values from 0 through 15. If we look at it in base 10, we can store that we can represent those 0 through 9 and then A through F in hex. To convert those into binary, we have 4 bits, because 1111, that maximum value of 4 bits is 15. So that provides us in binary to represent the values 0 through 15. Okay, so we convert all those, and you can see here you should be able to do the conversion in binary. Now we have to do the 2's complement, and once we've converted this to binary, we only do the 2's complement conversion if the most significant bit is 1. Okay, in this case, the most significant bit is in fact 1. So now what we do is we add 1. Okay, so we take, we convert, we flip every single bit, and then we add 1. So these are all, anytime you find a 0, you have a 1. Anytime you have a 1, you have a 0. Once you've flipped, okay, if this were a 0, we wouldn't do this. We would just have the value. But because this is a 1, it's negative, we flip all the bits, and now we add 1. Okay, so this is every single bit being flipped, so the opposite of what its original value was, and now we add 1. And from here, we just have binary math. So 1 plus 1 is 0 with a carry. This now becomes 1 plus 1, that's 0 with a carry. Okay, you can see we continue all of that. This becomes, at some point here, we have a 0 and a 1. So 0 plus 1 becomes 1, and now we have no more carries. So now we just move all those values down, and if we were to convert that binary number would be 6,000. Because this was negative though, we add the negative sign. And we can use things like our calculator to help. So if you see here, 6,000 as far as a binary number goes, 0000, okay, first 4 bits are zeros, then it's a 1110, 1110, 1110, 1110, and then a 1, that final 1, right? So at 6,000, we add the negative sign because that was stored in 2's complement. This most significant bit was originally set. All right, let's see. At this point, I want to try to keep these videos a little bit shorter. So I'm going to stop now. I'm going to create 2 more videos for this week, and that will be one that will look at the if statements and the nested if statement, and then an additional one that will look at loops and then switch and jump tables. Okay, so try to keep those a little bit down. Hopefully most of what we went over today was review, and that if it's just been a while since you've thought about it, this gets your, just thinking about those different instructions and some assembly here. Because again, that's going to be a lot of what we end up looking at. IDA, of course, is showing us a lot of assembly instructions, and that's what we're looking at. So if there's anything that didn't quite make sense, or you don't quite remember, or you just want to spend a little bit more time on as a refresher, let me know. Check the resources, look at that assembly book as a way to just kind of go back through and refresh, as well as some of the readings. The readings will do that as well from some of the books that we're using. So with that, I'll stop this video, and in the next one, we'll talk about if statements. Thanks.